Now that we know the derivative of e to the x, let's actually use this derivative in some examples. So to start with, let's say that f of x is e to the 2x, and let's just find the derivative of f. So we have to be a little careful here because this is actually a composition. So the tricky thing about exponentials is they give us yet another way, or they are a different way for compositions of functions to appear, right? We're used to compositions showing up in parentheses, especially when there are, say, other functions, other named functions, so that the inside of the parentheses is the inside. But exponents like this are the inside of an exponential function. So this is a composition. The outside part is the e to the something function, and the inside part is 2 times x. So to find the derivative, we have to use the chain rule. So the derivative of the outside part, the e to the something function, is e to the something, right? Because the derivative of e to the x is e to the x. So now we have to put the inside into this and multiply by the derivative of the inside. That's what the chain rule says. So put the inside into that, and we get 2x in there. And then multiply by the derivative of 2x, and that's 2. So this is the derivative with respect to x of the inside, which is 2x. So the derivative of this function is 2 times e to the 2x. All right. So one mistake that is very common is to think, well, if you have e to anything, when you take its derivative, you get exactly the same thing. And that's not actually true, right? It's only if the thing in the exponent is x, the variable x, that you're differentiating with respect to. Then the derivative of e to that is e to the x. If the thing in your exponent isn't just the variable, isn't the independent variable, then the chain rule spits out some other stuff. All right, for a second example, let's calculate the derivative of this function g, so e to the x times sine of x. Well, this is a case for the product rule, right? So the derivative, since it's e to the x times sine of x, so we need to take the derivative of the first piece times the second piece with no derivative plus the first piece with no derivative times the second piece with the derivative. All right, so the derivative of e to the x, of course, that's just e to the x times sine of x plus e to the x, and then the derivative of sine of x is cosine of x. All right, and then if we wanted to, we could factor out this e to the x. So e to the x times sine of x plus cosine of x. All right. For our next example, let's find the second derivative of e to the, this whole mess, x squared minus 3x plus 7. So remember, a second derivative is just the derivative of the first derivative. So e to the x squared minus 3x plus 7. So first we need to calculate the first derivative. So this is the second derivative. So what I'm going to put in parentheses here is this first derivative. So it's e to the something, right? So we have to use the chain rule. So the derivative is e to the same thing times the derivative of the stuff inside, right? The stuff inside is x squared minus 3x plus 7. Now, chain rule says we have to multiply by the stuff inside, and that's 2x minus 3. Okay. Now we need to take one more derivative, because remember we wanted a second derivative. But now we have a product here, so we have to do the product rule. So this gives us the derivative with respect to x of the first piece, which is e to the x squared minus 3x plus 7, times the second piece with no derivative, so 2x minus 3, plus the first piece with no derivative, e to the x squared minus 3x plus 7, times the derivative of the second factor, so derivative of 2x minus 3. I need a closing parenthesis here. All right. Now for this derivative here, well, that's actually something we calculated. That's this piece right here. So e to the x squared minus 3x plus 7, and then the chain rule spits out 2x minus 3. But that's an extra factor of 2x minus 3. We already had a 2x minus 3 plus e to the x squared minus 3x plus 7. And the derivative of 2x minus 3 is 2. Okay. So I guess to put this all together, we could factor out this e to the x squared minus 3x plus 7. And then simplify the stuff that's left. So here we have 4x squared, and then let's see, 6 minus 12x, and then minus 9 plus 2, so minus 7. And there we go. There's our second derivative. Of course, exponentials show up in lots of applications, in particular in modeling population growth. And here's a typical example. So suppose that the size of a population of insects in a lab after t days is given by this formula. And this is in individuals. Right? So this function tells you how many insects are in the population. How fast is the population growing after 300 days? So since we're asking how fast, we're looking for a rate of change, and so we should calculate a derivative. So first we need to calculate the derivative of this function, and we could use the quotient rule, but the quotient rule is annoying. So maybe instead we should write this p of t as a product. So 1000 times 1 plus 50 e to the minus 1 over 100 t to the minus first. Maybe that would be a better way to do it. Okay, so now we can take the derivative of this. The constant multiple rule says we can just copy down the 1000 here. Okay, and now we need to take the derivative of this second factor. We need to be a little careful because there are multiple layers here, right? There's the exponent, minus 1. Inside of that, there's this sum. Inside of that, there's this constant multiple. And inside of that, there's an exponential, which has its own inside. So we have to be pretty careful here. So all the way on the outside is this power function, minus 1. So bring the power rule says bring the power down and subtract 1 from the power. Now put the chain rule says put the inside into there. So 1 plus 50 e to the minus 1 over 100 t. And then multiply by the derivative of the stuff inside, which is 1 plus 50 e to the minus 1 over 100 t. Okay, so minus 1000. This stuff here, I'm going to put that in the denominator. So that's 1 plus 50 e to the minus 1 over 100 t squared, like that. Right, this negative exponent puts that in the denominator. And now multiply by the derivative. Well, the derivative of 1 is 0. And then, so we get a 0 plus something. So I won't write the 0 plus. And then the constant multiple rule says we can just copy down this 50. And then now we need to take the derivative of this exponential, e to the minus 1 over 100 t. But that's a job for the chain rule because there's an inside and an outside. The outside is the exponential part. So derivative of e to the something is e to the something, right? 1 over minus 1 over 100t times the derivative of the stuff inside. And the derivative of minus 1 over 100t is minus 1 over 100. Okay. So putting this all together, I guess we can do some simplifying with our constants. So 50 times 1 over 100 is a half. But then a half times 1000, that's 500. And then this minus sign and that minus sign actually cancel. So all together, it looks like we get 500 e to the minus 1 over 100 t over 1 plus 50 e to the minus 1 over 100 t all squared. All right, so there's our derivative. And of course, the units for this, since p, the original function p of t, is in individuals, right? Individual insects. And t is in, I think, days, I said. So this function tells us the rate of population growth in individuals per day. All right, we wanted to know the rate of change after 300 days, so we just need to plug 300 into this, which is going to be annoying. But that's life when you're working with sort of vaguely realistic applications, right? The numbers are never nice. So minus 1 over 100 times 300 over 1 plus 50 e to the minus 1 over 100 times 300 all squared. 300 times 100, 300 over 100 is 3, so. And then now it's calculator time for sure. So let's see what this gives us. Should have pulled up my calculator beforehand. All right, so 500 times e to the negative 3 divided by 1 plus 50 times e to the negative 3, and then square the denominator, and I get 2.0445. And this is individuals per day. All right. It's a little difficult to have any sort of intuitive sense of if this function looks correct. But what we could do is graph the original function and its derivative and see if it looks about right. So I have a graph right here. There's the original function. And if we type in our formula for the derivative, let's see, where can I put this to make everything fit? Nowhere, of course. Let me shrink this window like that. Okay, so our derivative function, which I'll call g of x just so that I don't have conflicting names. So it's 500 times e to the negative 1 over 100 times t, I have to call it x to make GeoGebra happy, divided by 1 plus 50 times e to the negative 1 over 100 t, or x, and then squared. All right. So let's see if this looks sensible. Let me make this a different color. How about there? All right, so the red line is the population function, and the blue line is its derivative. Well, you see, this red graph is getting so big that the scale, I had to make the scale like this so that the graph of the population function would fit on this coordinate axis. And we saw that the rate of change of this is like on the order of 2, which is so small that we just can't see it. So let's change the scale of the axis to see if we can see it. So there's the graph of the derivative. So it looks like at the beginning the rate of change is very small. In the middle, the rate of change gets pretty big. And then later on, the rate of change gets small again. That kind of makes intuitive sense because typically when a population is small, it's just so small that it can't grow very quickly. Once it sort of gathers some steam, then the population can grow faster. But eventually, you sort of bump up against the amount of resources available in the environment. And if your population is sort of using all of the resources that's available, the population can't grow very quickly because there just aren't any resources for new individuals. And so once the population gets big enough, population growth tends to go back down, and we're seeing that here.